Accuracy is defined as how close a measurement is to the true or accepted value. By contrast, precision is defined as how close a set of measurements are to one another. The easiest analogy we can use for expressing the difference between accuracy and precision is the bullseye. Here we have a set of measurements that are close together and directly on the target. And so therefore we would define this as both accurate and precise. In this case, the measurements are close to each other, however, they are quite far from the target. So in this case, the results would be defined as precise but not accurate. And finally, in this case, we see that the results are neither precise nor accurate because they're not close to one another and they're also not close to the target. So these results are neither accurate nor precise. In this slide, we have an image of spiral galaxy M100, which was taken on December 31st, 1993, with the Hubble telescope. Although this image looks quite nice, one of the quirks of the Hubble telescope is that when it was first launched, the images initially taken were actually quite fuzzy, much fuzzier than expected. This is an image of the same galaxy taken with the Hubble telescope 1 month before. As you can see, the image is much fuzzier than on the previous slide. The ability of the Hubble telescope to produce such spectacular images can be directly attributed to the main mirror, which is shown here during the manufacturing process. The mirror has a diameter of 2.4 meters, and it was precisely ground so that the largest imperfection had a height of less than 10 nanometers. To put this into perspective, if the mirror was expanded to the diameter of the Earth, then the largest imperfection would have a height of less than 12.5 centimeters. Now, the reason that the images initially produced by the Hubble telescope were so fuzzy is that the mirror was precisely ground to the wrong shape, effectively giving the Hubble telescope myopia, or nearsightedness. In order to correct this problem, the Corrective Optics Space Telescope Axial Replacement, or COSTAR, was installed by Space Shuttle Endeavour on December 1993. Here we have an example of precision that can be applied to the laboratory. In this case, we're weighing out a reagent using either a top-loading balance, shown here, which has a precision of 1 decimal place, and in this case will give us 3 significant figures in the mass. And on the right, we're weighing out the same reagent but using an analytical balance, which has a precision of 4 decimal places and will give us 6 significant figures in the mass in this case. Now, you might think that it's always better to weigh out your samples using an analytical balance because it is both more accurate and more precise. However, this comes at a cost of both expense because the analytical balance is much more expensive than a top-loading balance, and time because it generally takes you about 10 times longer to weigh out your samples using an analytical balance than it would if you were to use a top-loading balance. So, which balance should you use when doing your measurements? Well, it all depends on your application. If you're weighing out a reagent that you know will be present in excess, then you might as well use a top-loading balance, as it is both cheaper and much faster. And the exact weight doesn't really matter as long as it is present in excess. However, for the most exacting work, then you should always use an analytical balance because it is the most accurate and precise instrument. Now, this slide also shows the importance of significant figures, as the number of significant figures will help us to assess the precision of the measurement. In this example, we are asked to identify the number of significant figures in each of the following measurements. So, for example, the volume of 24 milliliters has 2 significant figures. The mass of 3,001 grams has 4 significant figures. A volume of 0.0320 cubic meters has 3 significant figures. 6.4 times 10 to the 4 molecules has 2 significant figures. And finally, for the example of 560 kilograms, the way this number is written is actually ambiguous, as it can have either 2 or 3 significant figures. If we wanted to clearly identify 3 significant figures, then we should put a decimal point after the number. Or we could write the number in scientific notation to clearly express 2 or 3 significant figures. When keeping track of significant figures, it's important to remember that all non-zero digits are always significant. What about zeros? Well, if the 0 is located before the decimal point, then it is not significant because it is only used for cosmetic purposes. Zeros before the first non-zero number are also not significant because they are only used to locate the position of the decimal point. Non-zero numbers are always significant, as we mentioned previously. Zeros between non-zero numbers, such as we see here, are significant. And zeros at the end of a number placed to the right of a decimal point are also significant. Now, when you are multiplying and dividing, it's important to remember that the number of significant figures in the answer is determined by the number that has the smallest number of significant figures. So, in this case, when we multiply these two numbers, our answer should have 3 significant figures because this number has the fewest number of significant figures, which is 3. In this case, I have included one extra significant figure, which I have indicated with a subscript, just in case we need to use this answer for calculation further down the line. If we want to report this as a final answer, however, then we should round up. So our final answer in this case is 11.4 centimeters squared. Notice that we've also kept track of the units. In this case, when we're doing a division, our final answer should only have 2 significant figures. And here, our dividing, our answer is 0.0407 kilometers per hour. Again, rounding to 2 significant figures gives us 0.041 kilometers per hour. So as I mentioned before, in order to avoid rounding errors, we always keep one or more extra insignificant figures in our intermediate answer until the entire calculation has been completed. When we're adding and subtracting, we have to keep track of the number of decimal places. In this case, when we add these two numbers, our final answer should only have 1 decimal place because the number here only has 1 decimal place. So adding these up, we have 11.43 seconds. You'll notice I've kept one extra significant figure in case we have to use this answer in another calculation later on. But rounding will give us our final answer, and we should have a final answer of 11.4 seconds, which only has 1 decimal place. Adding these two numbers gives us 68.45 seconds. Now you'll notice that once again, our final answer should only have 1 decimal place. However, in this case, when we round, there's an additional rule we have to remember. Because this number ends in exactly a 5. So for numbers ending exactly in 5, we round to the nearest even number. So in this case, our final answer to 1 decimal place is 68.4 joules, because 4 is the nearest even number. The reason why we round to the nearest even number is that this gives us an equal probability of rounding up or down. If we always round up, then we introduce a slight bias into our results. Here, when we're doing this subtraction, you'll notice that our final answer should have 4 decimal places. And in this case, our final answer is 0.8923 meters. Now, you might notice that because we keep track of the number of decimal places in addition and subtracting, sometimes we can add or lose significant figures. So the number here had 6 significant figures, and we're subtracting that from a number that has 5 significant figures, and our final answer only has 4 significant figures. And that's just what happens when we have addition and subtraction. In this example, we are asked to calculate the average of 3 measured concentrations: 5.54 molar, 5.58 molar, and 5.61 molar. And you might remember that in order to take the average, we simply add up the 3 concentrations and divide by 3 in this case. In this case, 3 is what is known as an exact number because it is a counted number. We know we have exactly 3 concentrations. And this is important because exact numbers are considered to have an infinite number of significant figures. So when we add up our concentrations, we should have 2 decimal places because our concentrations all have 2 decimal places. So adding them up gives us 16.73 molar divided by 3. So the question is, when we divide this by 3, do we get 3 significant figures or 4 significant figures as shown up here? And the answer is we only have 3 significant figures. So our answer is 5.576 molar, which we then round to 5.58 molar. The reason we only have 3 significant figures is that we also have to use common sense. We cannot create significant figures simply by taking an average. Our concentrations all started with 3 significant figures, so the average should also have 3 significant figures. The date is July 23rd, 1983. Flight 183 is Air Canada's brand new, state-of-the-art Boeing 767-200, which is en route from Montreal to Edmonton with a stopover in Ottawa. Unbeknownst to its passengers and crew, Flight 183 is about to run out of fuel about halfway to its destination at an altitude of 12,500 meters. Turning Air Canada's $40 million state-of-the-art aircraft into a 120-ton flying brick, which drops at a rate of 600 meters per minute. Fortunately, by a miraculous series of coincidences, the pilot and co-pilot are able to safely land the plane at an abandoned Air Force base in Gimli, Manitoba. Interestingly, the Gimli glider ran out of fuel due to an incorrect calculation on the part of the pilot. This calculation was checked 3 times, once by the pilot himself, a second time by the co-pilot, and a third time by the grounds crew, who were responsible for refueling the plane. Normally this calculation was done by the onboard computer. However, maintenance staff had previously deactivated both the computer and its backup computer, leaving the calculations to the pilot. Now the pilot had calculated that in order to reach Edmonton, the plane needed 22,300 kilograms of fuel. A dipstick test indicated that the plane already had 7,682 liters of fuel on board. Now you notice that these are in different units. So in order to do the calculation, we convert the volume to mass, which gives us 6,168 kilograms of fuel on board. Subtracting this from the amount of fuel required leaves 16,132 kilograms that must be transferred to the plane. Converting this back to liters means that 20,090 liters of fuel should have been transferred to the plane in order to safely reach Edmonton, Alberta. However, what the pilot actually calculated was that they had 13,600 kilograms of fuel on board. Subtracting this from the amount of fuel required left 8,700 kilograms of fuel to be transferred. Okay? And converting this back to liters meant that they had only transferred 4,915 liters of fuel, much less than was needed. You can see that the mistake arose because the pilot used the wrong conversion factor. And the reason he didn't realize this was that he didn't write in the units. So the take-home message here is always write your units when solving problems.